So I'm going to review with you some of the work that was done recently. I had the pleasure to participate in some of it, and the data was agreed to be provided to the council for presenting it, which is good. So before I start, a little bit of background. Before I start to be involved in high-performance computing, I was on the other side of doing simulations, and I was dealing with developing an artificial pancreas for diabetics. It was years ago, probably 13, maybe 14 years ago. And beside of doing that, I was also involved in teaching networking. And that's pretty much the part that caught me more. In 1999, when there were two groups of companies who worked on designing or creating or specifying the next generation of network solution. One of that group was called 3GIO, and the second one was Future.io. And at the end, those two groups combined together to something that's being called today InfiniBand. Now, InfiniBand was designed to be able to provide a solution that goes to high-performance computing, goes to large-scale databases, and it goes to storage. So there was all the elements there that are being required for all those areas. Things like lossless fabric, things like quality of service, things like RDMA, and other elements. And of course, when the first InfiniBand solutions came out to the market, the first users that jumped on it were from the high-performance computing, because it really delivered high bandwidth, much higher bandwidth, much lower latency. And of course, this is the first place that InfiniBand went to. Years after, enterprise databases start to look on that technology and start to adopt it as well. One good case, and the person from Xaratex is not here, but one of those companies, for example, is Oracle. And Oracle decided that InfiniBand is the best solution for their database appliance, which is being called Exadata. And recently they've extended that and start building clouds, which is called Exalogic, which is also using InfiniBand for that. InfiniBand helps Oracle not to have an incremental performance gain for database applications, but they were able to show between 10x to 15x performance improvement with InfiniBand. So it's an order of magnitude higher performance. So InfiniBand is a great solution that can fit multiple areas, and definitely is a superset of things. And as a superset of things, when you want to optimize that for a specific usage, you of course need to pick the right things from that superset and use them in an effective way. And this is what I'm going to show you here. So first, as part of being used in high-performance computing, InfiniBand can use for small scale, and then reduce, for example, the number of servers that you need to use for a specific performance. So there is some cost saving with it. Of course, for the mid-range systems, and definitely for the larger scale. Today there are 7 petascale systems in the world. 4 of them are using InfiniBand. Out of the 7, 2 are the SMP way, and one of them is a proprietary interconnect. But 4 of the 7 are using InfiniBand for the networking, which shows that InfiniBand can definitely deliver performance in a very high scale environment. So for the information or the data that I'm going to show you here, there was a project, which I have more information the next slide. But that project looked on HPCC benchmark. An HPCC benchmark suite, it's a good benchmark suite to evaluate systems because it's combined multiple testing or multiple benchmarks. There are benchmarks that measure CPU capability. There is benchmark that measure bandwidth to the memory. And there is a couple of benchmarks that measure latency. And if you, for example, are going to go to Cray website, you're going to see some information about the importance of those two tests out of the HPC challenge. One of them is the MPI random ring benchmark, and the second one is MPI natural ring benchmark. Those important benchmarks for evaluating capabilities of systems. And I definitely agree with what's there on the Cray website. You can find some information in other places. And those two benchmarks was in the main focus of a project that was looking on InfiniBand and optimizing InfiniBand to look into getting the highest performance with those two benchmarks. So this is the note. The following project was done between several organizations. Mellanox was part of it, Lawrence Livermore National Lab as well, OSU, and Vapich MPI. Now the project was looking on InfiniBand verbs interface. InfiniBand verbs interface, this is the InfiniBand interface as specified in InfiniBand spec. So someone, yesterday Sharon, I think talked yesterday, or the day before, talked about free software, that it's not really free, and I agree with it. There is nothing free in the world. That's something that I learned. And sometimes free things cost you much more than non-free stuff. But there is a difference between free and open source or standardizations. Open source is a great thing because open source helps or enables multiple organizations to work together. Now, folks who's taking open source codes or solutions and then pass them throughout qualifications and give support and stuff like that, they can sell things that were designed in open source, and that's kind of combining the best of both worlds. So the InfiniBand spec defines InfiniBand verbs as the interface. And that interface enables database applications to run much faster. That interface enables high-performance computing to run much faster. That interface enables storage, a file system, to run much faster than anything else. But the thing is that if you want to take that complete interface, which is a superset, and run it in a very large scale, performance optimized HPC system, you need, of course, to do the right modifications or the right setup around that interface, make sure that all the setting of things is correct. And with that, you can do wonderful things with it. So I definitely want to thank all the guys, all the folks that were involved in that project and allow me to present the results. So first, there was some work that was done on the low-scale things. The reason was to look into not only optimizing in a very large-scale systems, but also what happened when you run 8, 16, 32-node system, going to the small scale. For the small-scale tests or testing or development, the system that were used are the system from the HPC Advisory Council Center. Now, the center consists of multiple systems. There are systems that are CPU only, x86. There are systems that have GPUs inside. So there is a system with NVIDIA GPUs. There are systems with ATI GPUs. There is a Lustre file system that exists. And then all the systems are being connected throughout a single fabric, multi-tier of a single fabric. And that was the base for the testing on a small scale. And I think I can jump into the first results. So the first results for natural ring latency, which is one of the tests. What we did in the beginning is we took the default MPI. Open source, free. You go and download the default, the MPI, and run it as default. And this is the results that you see. It's a nice low latency, but when you increase the number of cores, the number of processes, then the latency increases. Which maybe in a small scale you won't see much of effect, but definitely when you go to the large scale, the effect's going to be much higher. So when you take the verbs interface and set it up correctly, and make sure that the MPI library and the drivers are being configured correctly, which means that you utilize the resources that are available in the right way. That when you open connections, you open them in the right way, and so forth. Now, from the application perspective, there's nothing that you need to do. But from a driver perspective and the MPI library, there are several tunings that you can do. And one of the things that I think will be done is provide a full configuration and information to anyone else who wants to reproduce the same setup. And with that, you can achieve a flat line of latency, which is basically the best scaling. There is a jump between 8 processes and 16 processes. And if someone can let me know why, that will be good. If not, I'll need to say it myself. But exactly. So 8 processes, this is a single node. So this is when you're running MPI on a single node. When you go to 16, this is 2 nodes, basically. And you have a multi-tier fabric. Therefore, there is some latency increase when you go outside of the box, exactly. But then you basically keep a flat line of latency running on top of InfiniBand verbs. Same thing with MPI random ring latency. Same configurations, starting with a default MPI setup. Again, you see that latency increases with the number of processes, which is not the desired solution. And then when doing the needed setup of things, then you can get a flat line. So that was great for small-scale testing. And then we moved to do the large-scale testing. One of the systems that is accessible to do development, do optimizations, and do some testing is the Hyperion system at Lawrence Livermore National Lab. It was a system that was built through funding of multiple companies. Intel, I'm trying to remember names. Intel, I think Red Hat was a part of it, and multiple other companies, DDN, a few others, as well as Mellanox. And that's enable us to get access to that gear and InfiniBand verbs latency. You need to activate Windows. Now it's an open environment. Therefore, it's not a system that basically you take and put it in a HPC and put lightweight kernels and stuff like that. Kernels are not that lightweight here because it's enable multiple access and multiple application development. But still, it's a very nice system. You see the topology here, multiple tiers of switch fabrics. There is file storage, running Lustre, as well as not small number of nodes in that system. I think it's in the range of 1,100 nodes, the entire system. Now that system, I think, is around 2 years old. Something like that. It's using Intel Nehalem, so it's even before the Westmere. So the previous generation, and even there is a mix of two different CPUs. So it's definitely not the optimum place for doing large scale, but still it's a good place for doing development. Now I did the end. By the way, the arrows work right. So this is after doing after optimizing MPI or OSU in Vapage with OSU on Hyperion. I don't have the before, but you can definitely imagine the before if you're just taking a default MPI and running. And with the right setup, you basically see the same. So this is a natural ring latency going through nearly 4,000 processes. And again, it's the same effect. And it gives you a flat latency. The reason for the more increase in the beginning, of course, there are more tiers of switches or switch fabric for that system. And pretty much the same for random ring latency. Now, with those optimizations on top of verbs. And again, verbs is a great interface because it gives you all the flexibility of or the ability to do multiple things, either for databases or storage or IPC or MPI. So this is basically a result of taking that superset of interface and optimizing that for MPI usage. Now there was several applications that were run on top of that setup, or on top of that optimized setup, to look what is the effect of the optimizations that were done for those random ring and natural ring tests. What's going to be the effect on the application from the other side? Some of those applications, the data distributions around them is not available to present, but one of them is. And this is the results of one of the most used applications at Lawrence Livermore and other national labs in the US. Application is AMG. And that's the results that were completed in December of last year, so not long ago. Going through nearly 4,500 processes. And I don't have the before, but you can imagine what was the before of the performance. But after all the optimization, AMG was showing a linear strong scaling on that system. It's an open system, so it's not really optimized for large scale at the end. But still, when you take in an interface and you know what you do, and part of what we are pushing from the council perspective is to open that modification list to everyone, so it can be repeated. You see a very impressive performance on top of verbs. Let's see if I have anything else here to share with you now. So this is a nice use case of using InfiniBand verbs interface as defined by the spec. Which is good because it's provide not only the standardizations, but also the ability of multiple vendors to collaborate together around open source. And it's also enable afterwards vendors to take the open source results, pack them and sell them, so you don't get something free without any support, as Sharon said before. If someone is interested to try some of the setups before, we will be able to have some of the things published as a list of items that needs to be configured. You're more than welcome to catch me, and we'll try to do our best.